Yesterday, I made a fake game, made a mock-up of a game, and I discovered that it's actually kind of hard to mock up a game. If I had more cars or more roads, I would have definitely just gone and implemented the game. I wouldn't have bothered to write all these little scripts. So let me show you how this works. If you want to watch yesterday's video for context, this is a game engine that I'm working on, and this is the draw task. And down here, I'm drawing a bunch of meshes. It's just X, Y, Z, and a rotation value. And these meshes are defined at the bottom. And I have some procedural generation routines to generate these meshes. Mostly they're just boxes. And this is just developer art. This is just a demo. There's no actual game here. But today I want to make this a little bit more real. So what this car does is there's 2 seconds of the little green person walking. Then there's 1 second of the car driving in the person's driveway. And then this code is more similar to how it would actually work in the game. And what I'm going to do is convert this part of the if statement, this part of the if statement, these two parts of the if statement to look more like this and create splines, which will just be straight lines. So you can, this is the thing about curved roads, is once something is a spline, once something is a curved shape, then everything has to be a curved shape, even the straight lines. Now, I mean, in principle, we could do an optimization and make, straight roads and curved roads. But in the original game, the cars always traveled along splines because at the intersections, when they made a right turn or a left turn, that was a spline. And so when they're traveling along the straight roads in the old game, they're really traveling along a spline that's just a straight spline, a spline that doesn't have any curve in it. So we're going to convert this driving in the driveway part, this parking at the mall part, into splines. And we're also going to implement the movement of the person. And we're going to make those splines. And there's going to be the start of a traffic graph, a graph of the layout of the transportation infrastructure, including pedestrian paths. So this is the start of a multifaceted transportation system where we have pedestrians, we have cars, we have mass transit, we have freight, we have airplanes and everything. And it all starts with just getting the structure, getting, the different splines. Alright, so just going to make a few splines here. This one is the person walking from the house to the car. Now I wonder if I set the control points to just be the same as the start and the end, will that give us a straight spline, or will that just give us some weird behavior? I don't know. Now we have the car in the driveway. It must go from 330 to 300. Then we have the car driving along the road. The road ends at negative 300, and the car continues driving. How far does it drive? I'm actually not sure. Well, I guess it's in line with the other parked cars. I parked at negative 360. So it goes to negative 360. We want to set the control points the same here. Let's see, the pedestrian actually makes 3 moves after this. $360, negative 30. How far does he go? Kind of did the math funny. So I'm not really sure how far the pedestrian goes in the X direction, but let's say negative 30. That seems like too much, but we can start there. He actually, before he moves there, I think he moves a little bit more in the Y direction. Negative 360, negative 380. $380. And then one more move. He goes from here to he starts at, and let's say he goes to 400. 380, negative 400. So now we have a series of splines that our character can travel along. Okay. Before we get to that, we have to think about the character moving along these splines. So the character will start here. There'll be kind of a physics simulation of the person walking. So every frame, there's a duration. The character can move a certain distance along the spline in that duration. I think we have to figure out how long these splines are. That's weird. It tried to answer the last question even though it was kind of fine. Alright. Calculating the length of the spline. Length of a curved spline is longer than right. Approximate it. I wonder if there's a different spline algorithm, or maybe we can kind of, prepare the splines, like pre-compute some of these values. Because I don't want to have to compute this every frame, but for right now, I think it's just fine. Such a creates. Yeah, okay. Let's go ahead and put some of this code. into our spline class. Calculate spline length. Set this to 48 to match how we actually, because we have 48 down here, and probably this will become some sort of global constant, and maybe it'll be integrated into our database, but who knows. Okay, so we're going to calculate the spline length. This function seemed useful too. Maybe we can put this at the top. Because I was just setting the control points at the end. But this will certainly be a lot less tedious than, because we're probably going to have to adjust these values. I probably made a mistake somewhere. Then the end point is 330, 0. And now for this kind of thing, I really should use AI. So hopefully I'll get my copilot here. Yes. So it goes from 330 to 300. Then we have the road spline, which can stay the same. Negative 300, 360. When you use Copilot for this, you make less mistakes because the Copilot just doesn't make quite as many mistakes as I do. Negative 30. Hold on. I think we're missing one. Maybe it's not a good idea to delete the code before letting Copilot take a look at it. Okay, negative 300, 360. What's going on here? $380. I think we want this day kind of at 0, or maybe we want it at 3, because I think I put the person 3 spaces over. Or probably negative 3. So this one relates to the person, this 3 relate to the car, and these 3 relate to the person walking through the parking lot of the mall and into the mall. This one to be negative 3. Okay. Now, our draw function has kind of become an update function, that it's updating the animation, and it's going to be updating the physics. I'm going to forgo using storing things in the database and separating it out into tasks. I'll do that as a second step, but right now, I just want to store kind of like a progress value. Is that how I want to think about it? Well, I guess it's there's like an I-32 segment equals 0, and an F-32 progress equals 0. So I'll do some code here that will just kind of update the segment and progress variable to march along these spline paths, but it won't. This script code will remain, so that nothing will happen in the drawing. It'll just be some numbers that are updating. Okay, so I'll put it in a little block here. So update position along path. So spline path spline equals segment. Let's see, what was the name? Calculate spline length. Put that here. Path length equals calculate spline length. Path spline, and number of segments can go to the default. Yes. So progress plus equals car speed. I'm actually going to call this car speed 2 because we want to. This is probably going to be something else. So it's dir times, and if progress is greater than path length, progress minus equals path length segment plus plus. Okay, good. And we just want to see if that compiles and doesn't crash. Of course, it doesn't compile. How many do we have here? Can I count today? A little tired. Okay, so it's 7. Calculate default argument given for parameter 2. Previous specification. Oh, so I guess I can't put this default argument in both places. Okay. I'm going to go ahead and remove some of our printf debugging. Okay. Okay. So the first segment and segment greater than 5. Actually, maybe we do this differently. Marlog equals. So the car is in a fixed location at the start. Again, we're just mocking this up. I think that's not where the car ends up here. Negative 360, 0, negative 360. 360. equals loc on path. Sure, so the person will be inside the car, but it will be overlapped. Now let's see, does this work? Let's put a little bit of printf debugging here. See what's going on. We want to know what the path length is. Actually, this should really be seg length. It's the length of the segment, not the whole path. So apparently it's just very slow. Which seems like it should be 1 meter a second. I don't know why it would be so slow. Hold on, how did I do this? Oh, I see. I'm using 2 different variables for the car speed, because I don't want to delete my old code yet. Maybe this is a bad habit of mine. I create new code before deleting the old code, because I don't want to lose the functionality. That's still quite slow. Still quite slow. Okay. There's some glitching at the start and end. Looks like the car stays on a little bit too long, so it's this should be greater than 3. So other than some glitching, this basically works. Let me go over what's happening again. So we have a list of splines. This middle one represents the curved road. The other ones represent walking through driveways and parking lots and so on. Every frame, it looks up what spline it's along. Well, I noticed something strange here. The segment gets updated, but we really should update the path spline. And then the segment length. I wonder if that'll fix the glitches. Let's see. Ah, that looks much better. I'm surprised at how high I have to set this car speed value in order to make it work. Let's do this. 32 move speed, and let's say that the person goes 20, which seems way too high, but okay. And then if it's the car, then move speed equals 50. And this is move speed. So the walker, the pedestrian and the car are going to go at different speeds. Okay, that seems quite natural. For some reason, we're actually just not getting the person here. So we can draw the person all the time, and the person will just be inside the car. And it'll just be overlapped. You know, as an optimization, we obviously wouldn't do that, but for this demo, it's fine. So the person mesh is actually inside of the car, which is quite nice, I guess. The path that the person takes through the pedestrian mall is screwed up, so Copilot did not save the day today. I think Copilot actually caused that error. So, let's figure out what this person's supposed to do. So the car parks just fine. Then I want the person to go from next to the car. And he walks towards the mall. I think this should be 370. Oh, and then here he starts in the wrong place. All right. We got a person on a car. Drive the car along the path. He gets out, and he goes into the mall. Nice. Very nice, very nice. Okay. So, one little detail that we've lost in this transformation is the bus. So I put a little bus in there just so that there's something else going on besides the car and gives a suggestion that there's more going on to this demo. So the bus only matters in segment equals 2, I think. Then F32 bus progress equals seg length minus progress. And AI is just going to do everything for us. That's so easy. Now doing it this way, the cars are going to look like, the car and the bus will look like they crash into each other. Let's see if we get that bus. There it is. And crash. Terrible. So we can fix this with just a little trick. So how did we do this down here? So I just did some trigonometric calculations. This tangent value is a direction going along the path, in the direction of the path. And we want a vector that's perpendicular to the path so that we can shift the car over and we can shift the bus over so that they don't collide. So the car will appear to be driving on the right side of the road, and the bus will be driving on the right side of the road from its perspective. Okay. So, yes, we did this car log plus, this value based on, there we go, negative road offset. I think this road offset, we want to, there we go. I wonder if this is, one of these has to be positive, and the other should be negative. And person loc equals car loc. There we go. That looks good. There's the bus. Very good. I wonder if they feel like they're just a little bit close. When you actually look at cars driving on the road, they do look like they come very close to each other. But maybe that's a little bit too close for comfort. Let's give it a little bit more. That looks very good. Very natural. Very good. So, I've accomplished the objective that I set out to do yesterday. We have house, person, car drives along, goes into the mall. We even got the sign, we even got a bus coming the other way. So I'm not really sure where to go next, but I think that maybe my area of interest and what I think might be visually appealing is if we started to get into actually routing and having a transportation network. And I can procedurally build a grid, and then I can randomly generate some cars, and the cars can travel along the grid in random ways according to some routing algorithm. That somewhat requires me to start thinking about how do I want to represent things. Do I want to have representations of the intersections here? In the original game, there were edges, which could be called road segments, and there were nodes, which could be called intersections. And before I start, programming and making distinctions between nodes and edges or road segments and intersections, I want to think critically about what I want the final game to be and what kind of state that I want to represent. And if you think about, kind of a busy city, let's say that you've got, some intersection that's in the center of a city. You've got some buildings along here. You have pedestrian paths. You have crosswalks. You have sidewalks on both sides of the road, and pedestrians have to go across somehow. You're also going to have entrances to, like the metro system. So this might be like a staircase leading downwards into a subway. You have bus stops. And if we think about all the different types of paths that we have in this situation, we have various pedestrian paths. Walking down here, going into the subway, going to wait at the bus stop. The bus comes, they have to go into the bus. We have a bus here, maybe. The bus has its own kind of paths. It has, a line a transit line that it follows from stop to stop. That's a path of a sort. It might be represented differently. Obviously, we have cars that have paths going in both directions. And in the original game, all of the cars followed very rigid paths. They were basically on railroad tracks. And that makes sense in a rich country where people follow lane lines and don't cross into the other side of the road. But, there are other countries in the world where people drive differently, and they, it's more like full-on collision detection, where there's just these kinds of entities, these agents that move through space, and they take up a certain amount of space, and they avoid colliding with each other. So you could think about all the cars and buses and motorbikes and people on bicycles as, being able to occupy kind of a space. So a car might go kind of anywhere within this space, and it'll just try to avoid colliding with other cars. Especially a small vehicle like a bicycle, it might take kind of a chaotic path and flowing through different things, and, like we may simulate some entities as having, not having kind of a hitbox, so they'll avoid larger entities like buses. So they'll flow around buses, but they themselves don't take up any space. So they don't have collision detection with each other. And that works well for pedestrians, because you can imagine you could have like a whole crowd of pedestrians here. And, they can get pretty close to each other. And for the purposes of a physics simulation, it doesn't really matter all that much if they collide. Now, there's another factor going on here. When I programmed the physics simulation, the traffic simulation for the original game, New City, I discovered that the traffic worked pretty well if I had kind of like a density value for every road segment. So if a road segment is full of cars, it has a high density value and the cars flow slower. And this makes it kind of like a fluid simulation, like it has a pressure value and a density value. And that will work quite well for pedestrian pedestrian simulation without collision detection. So the people don't collide with each other; they can clip into each other, and that's okay. Maybe visually it'll look a little weird, but I think it'll be okay. And then we don't have to do full-on collision detection for all the pedestrians. But they can, if there's a place where there's a bunch of pedestrians crowded together, they'll move quite slowly because they're there's a high density in that area. There's kind of like a high pressure in that area, so everything moves kind of slowly. So in New City, there were edges and nodes, like over here that I was talking about before. But there was also this concept of lane blocks and lanes. And so, lane blocks are like this blue rectangle that I drew here. It's a block of lanes that are going in a particular direction along a road segment or within an intersection. So within this intersection, there'd be another lane block that goes from here and kind of curves around, and that's for turning right. And then there'd be another lane block that goes straight through the intersection. So I might try to... I think that the lane blocks are kind of the ultimate level of resolution. And this is kind of what it comes down to, is what resolution do we want to simulate the city at? If we simulate it all the way down to the pedestrian levels, and I thought about, like, we could even simulate, the pedestrians go inside the buildings and the buildings have an internal graph, which works quite well with, how we're thinking about these parking lots, so that there's an internal traffic network within this parking lot, essentially. You go down this driveway, and then there's some paths, and there's some places you can park. And so, the routing simulation, the traffic simulation will go all the way down to the parking lot level, and then the pedestrian will pop out, and there will be a pedestrian simulation walking through the parking lot and into the mall. And we could even do that inside of the building. And so buildings could become a kind of road segment that just has, building graphics as opposed to road graphics, and the people are inside the building. Now the question is, do we actually want to simulate that level of resolution? Because it could get, quite performance sensitive. And there's a lot of optimizations that you want to run. Like, if the player is not actually looking inside the building, you don't want to bother simulating and rendering all those people inside. The reason why I think about the possibility of rendering the locations of people inside of buildings is because I've thought about how to simulate an airport terminal. And if you think about an airport terminal, you have an airport terminal is a quite interesting thing to think about, because there's kind of like a roadway that comes into the airport terminal, and there's a drop-off area. And then there's the terminal building. And actually there's like multiple buildings, and maybe there's like a security gate here. In the modern day, there's a security gate. I guess security gates have been around since the 70s probably, but after September 11th, this became a much more significant feature of the airport. And you actually, if we wanted to simulate people inside, they would, flow through, and then they would flow down, and then there'd be a gate here. Let's put it on this side. And there'd be like an airplane sitting here. And the airplane will be parked in the same sense that the car is parked at the mall, or the bus is waiting at this bus stop to load passengers. So the person maybe parks too. The person kind of parks in a seat in the airport. And then when the airplane comes, they go down, and then they go into the plane. And then we probably stop, you know, I was thinking hopefully we're not simulating people like traveling along the plane. We're not going to get into that. But, you know, they go inside the plane and then they're in the plane. And then the plane, you know, has its own traffic network. You know, it's got a tarmac and then what is it? Taxis. And it goes down the runway and then it takes off. And then how I was planning to do airplanes in the game is, you know, if you've got your city and you got, you know, the airport here with a little control tower, and you've got planes taking off. You want the planes, you want to have kind of like a route for the planes. So you would create, you know, like waypoints and air paths that the planes have to follow so that they don't fly over the city. And these paths would have a high pollution value. So you'd want to put it under, you know, across parts of the city that you don't value or you're not using. So you could actually like choose where planes fly in the city. So ultimately, I think that we want to, you know, all of the stuff, the buses, the metro, the pedestrians, the transit lines, the planes waiting to pick up passengers, people walking through the terminal buildings. I think that we want to, you know, generalize this into one concept that can handle all of these different cases. Well, quite a lot to think about.